Hey, it's Xavier. I'm going to be solving one of these problems for extra credit in this video. I'm going to point my phone down, but I'm just showing you, it's me now. I'm going to be solving the work down here. I just don't have the capabilities to set it up nicely, to show my face and my hands and all that. I don't have the space or the technology for that. So I'm showing you me now. Then I'm going to angle my phone downwards at the work. All right, yeah, I'm going to angle it down now. All right, here we are. So we're looking at this problem here. I copied it down exactly onto this piece of paper, just for the sake of simplicity, because it's cleaner than this. So let's take a look at this. Same problem. So before I even read this, before we even look at this part, the numbers, we've got a car going around a curve. So it's like a car going around a racetrack. But with a lot of racetracks, they're banked upwards. That means the track is at an angle. Because if you're going very quickly around a track and you make a sharp turn, if you're going very quickly around this corner, for example, well, not a corner, but if you're going quickly around this bend, you're going very, very fast, you're just going to keep flying forward if it's totally flat. If it's completely flat, you're just going to fly off the track. So that's why with like NASCAR, for example, the tracks are actually banked inwards. They're at an angle, like right here. So it's kind of hard to show in this 2D drawing, but like I won't draw that with a pen, but like the track is tilted at this angle. Obviously not this extreme, but at an angle. This way, when you go very fast around a tight turn, you won't fly right off the track. You'll stay on the track. So that's kind of a situation we're looking at. So we've got a car driving along a curve at a speed and with a radius, and the track is banked inwards. So what we're trying to look for is the speed of this car, the velocity, the speed, how quickly this car can go around this track without going up this ramp. So we want it to stay the same place in the y-axis, the y direction. We want it to stay in that place. But before we do that, well, in order to figure that out, we have to look at some of the forces acting upon this. Let me draw us a diagram real quick. There's our angle. Those lines signify friction. And this is our box. This is our car. This is our mass. So to understand this, we have forces acting upon this car. This car is going in a circle, so we have centripetal force on this car. This is the force going in motion around a curve with a radius. That's centripetal force. But to understand that, we have to look at a couple other forces that are acting on this car. So the centripetal force of this car, the forces on this car going around in this curve, should be equal to the other forces. It's the sum of all forces. So let's look at the normal forces that are acting upon this car, not the like the speed, for example, not the gas propelling it. We're going to look at the other forces. So first of all, we have gravity. We have gravity pulling this car down. So that is drawn by mg. M is mass, G. So it's the Earth's gravitational pull, G, pulling down the mass of the car, mg. So that's M times G. That's the weight being pulled down. But we also have a normal force. And what this normal force is, it's the opposite of the gravitational force pulling down. We know this because of Newton's laws, saying there must be an opposite force to this action. I think that's Newton's second law. I could be wrong. It's Newton's second law or different Newton's law. But we must have an opposite force equal to this. That's why this pen isn't just going through the floor or coming up for whatever reason it might come up. Because it's being pulled down by gravity, but also has the normal force acting upon it, pulling the other direction so it stays in place. It only moves, though, when an external force, like my hand, moves it. But otherwise it stays in place because the gravity and the normal force cancel out. So normally that would be straight upwards. But because we're at an angle here, the normal force is kind of in a slightly different direction. So we have the gravity pulling straight down, but our normal force is kind of going like this. In that direction, let's call that n. To find this, though, we can break this up with trigonometry. There are a couple different parts. So let's make this a triangle. Boom. ny and nx. Let's redraw this triangle right side up. N, nx, and ny. So these nx's and ny's should be equal to, well, let's do nx first, equals n sine theta, which is the angle. These are trigonometric functions, trigonomic functions. Sorry, hold on, so n x equals n sine theta. And for ny, it's going to be n cosine theta. So those are the parts of our normal force that are pulling up. Those are important. But there are also some other forces here. So we've got gravity pulling down, and we've got the normal forces, and we broke that up into these components with trigonometry. We also have a frictional force, which is how rough, so this surface is rough, and a car driving over a rougher surface will need more force to overcome it. If you're pushing a cart along a totally flat wood floor, it's going to be really easy, it's smooth. But if you're pushing a cart over some bumpy rocks, it's going to be a lot harder. You're going to need more force to push it forward to overcome that friction. So that friction, that is what friction is. And friction has a constant depending on the surface, but here we've got its friction is mu equals 0.43. We'll get back to that later, but it has that constant. It changes between like surfaces and all. So friction is equal to mu whatever. Mu s equals the number. And that friction is this way. It's also directional. I'm going to call that F, force of friction. And because we're on this angle here, we can also break that up into another triangle. But instead, it's kind of not going to be quite this. It's going to be nx and, F. My bad. F, force of friction x, F, force of friction y. But we don't have the same triangle because this is going that way. This is kind of going out the other way. So for f of x, instead of sine theta, it's going to be cosine theta. But we're going to multiply that by the friction constant, so which is represented by the variable mu, the frictional constant between the surface of the road and the car. That has a friction constant, how rough that is, and the force you need to overcome it. It's not that exactly, that number is part of that. So that will equal, because we've got a different triangle here, remember it's a different triangle than this, n cosine theta mu. That's all kind of, yeah, it's kind of like a U or a 4. And F, and then friction force of y is equal to n sine theta mu. That's awesome. So now we have the forces in this section. We've got mg, our gravity. We've got our normal force, the opposite of gravity. And we have our friction. But we also have, talked about in the beginning, was the centripetal force. The centripetal force is the force of this car going around the circle, going around the curve. It's the force of going in a rotation. So, and we know this, I'm going to write this as force centripetal Fc. And we just know that this is m v squared. Well, we don't just know that, we can prove it. But what this is saying, force centripetal is equal to mass times the velocity squared over r. So this is saying the centripetal force of going around in this curve is related to the mass of the vehicle, or the mass of what's going in the circle, the velocity of what's going in that circle, and the radius of that circle. So that's what centripetal force is related to. So we know this, and we have these components. But what we can look at now is the sum of all forces, because we're trying to find the velocity here, but this should be the sum of all forces. So we're going to say f of c, which equals mv squared over r, equals the sum of our forces in the x direction, because it's going on a horizontal track and we're staying in place where we're driving straight. We're not going up or down. Yes, we're on a curve, but we're not going up or down. We're just driving straight. So we're going to look at the horizontal components. So that would be the x components. So this centripetal force should be equal to the x components. So that would be nx here, and that would be nx here, and f of x here. So we're going to say that's equals to n cosine theta plus n sine theta mu. That was, hold on, I made a mistake there. Ignore that. That's n cosine theta, and this is n sine. That was my bad. So n sine theta mu and n cosine. So n sine theta plus n cosine theta. Great, but we don't actually know what n is. We have to solve for n. We have these different components for n, but we have to find that out. We have our centripetal force, because we're going straight, flat. We're going flat equals these x components. But we also have to look for the y component, because that's what n is. Because n is the opposite of gravity, gravity is pulling down, and normal force is pulling up, that means it's in the y direction. So we just looked at this x direction here. Now we need to solve for this y direction, which is n. We have the parts for n, but we need to figure it out exactly. So how do we do that? We take our y components. We have our x components there, and then now let's look at our y components. So we have n cosine theta. We have n sine theta, n cosine theta, n sine theta mu. I'm messing up again. Sorry. N cosine theta and n sine theta mu. And then we also have mg. So what this should be equal to, so we need to look at those. We have mg, so m, actually I'll write this the other way. So we have our f of y, so let's say these are our x components, x, y, equals, these are actually going to be subtracted from each other. Our n cosine theta minus n sine theta mu. These are subtracted to each other because, going different directions. Minus mg. We can rearrange this, add this to both sides. We have mg equals n cosine theta minus n sine theta. That is our y component. But now we're still looking for n. We can factor this n out. N cosine theta minus sine theta equals mg. Then divide that out. We do some more algebra. And we get n equals mg over cosine theta minus sine theta. So that's our n value. So what we can do here is plug this n back up to here in this equation for overall centripetal force, because we're looking for the velocity of this, and that needs to be, we're looking for velocity, we need to solve that by finding the other things. Let's plug this into this equation. So we've got n sine theta plus n cosine theta mu. Oh, that should be a mu also there. Equals mv squared over r. Let's factor out these n's, so n sine theta plus n cosine theta mu equals v squared over r. And then plug this n in here. We have mg over this. So mg cosine theta minus sine theta mu. Sorry, that was times this stuff here. Sine theta plus, that shouldn't be there, cosine theta mu. Over r. Let me grab a different piece of paper now to clean this up. And our original problem said we're looking for velocity. Actually, before we get into that, I'm going to multiply this out a little further. Where should I do this? I'll do it. Yeah. So we're going to multiply this out a bit further. We have our mv squared over r equals mg cos theta sine theta mu sine theta theta mu. Let's multiply this out. That'll be mg sine theta plus mg cosine theta mu over cosine theta minus sine theta mu, which equals mv squared over r. All right, now if you remember the original question, we're looking for the velocity at which this car can go without sliding up. And by the way, when I did this down here, I was making sure the y direction was staying still, so it would equal 0. This whole thing should equal 0. That's also the point I was stressing. That's why I subtracted these. I forgot to mention that. I said I was subtracting them because it's going a different way. I subtracted these y forces because even though it is going a different way, but it's equal to 0. So all this stuff should equal to 0. But why? So let's just keep that in mind. We want that to stay in place. I forgot to mention that. Let's just jump back here. So we want the car to stay in the same place, and this is set up for that to stay in the same place, direction-wise, but what speed could that go at? Now we just need to solve algebraically for this. V squared right there, that's our velocity. We just need to solve that. We can cancel out some m's. Those all cancel out. We can do some multiplying and square rooting. So now we have v equals square root to get rid of that, and to get rid of that. R, because we're multiplying r, so r, g. And also, by the way, I can take this g out and this g out, so it's 1g and rg out there. Sine theta plus cosine theta mu. On top of this same stuff here. So we multiplied this, and we're going to square rooting. It's all on top of this same stuff. Cosine theta minus sine theta mu. That's awesome. We have our v equation now. Now all that is left for us to do is to plug in the numbers from this problem. So we had a 2,510 kilogram mass. We're going at a radius, well, the radius of the circle, remember, because we're in a curve, is 50 meters. And the radius is important because that's what the centripetal force is related to. The coefficient of the angle that the track's at, remember, we're angled. Theta equals 30 degrees. And then our friction coefficient, mu s, equals 0.43. Now we have all these numbers. We have r, we have m, which we don't actually need, g, theta, mu. All we need is that. So let's plug these in now. So v equals R is 50.0, G 9.81. That's just the strength of gravity. That's just the Earth's strength of gravity, 9.81. Sine theta, and our theta in this case is 30, plus cosine theta, which is 30, and then our friction coefficient, mu, which was 0.43. Let's plug in this stuff. So cosine 30 minus sine 30, 0.43. Actually, need to make sure I have enough parentheses. Now all that's left is to plug this into a calculator and solve for our answer. Let me do that very quickly. I actually did this earlier just to check that I was getting the proper number. So we're going to get square root 9.81 times our 50, so that's our R times our gravity, R times G, times sine 30 plus cosine 30 times our friction coefficient, 0.43, close that parentheses, close that parentheses, close that parentheses. Sorry, I'm just checking I have enough parentheses to make this work. Then our bottom half we're dividing, so cosine 30 minus sine 30, 0.43. And boom, that comes out to being 25.63. And we have to keep in mind the units on this. And this is velocity, so it's in meters per second. Which, because velocity is distance, meters over time. We also can simplify this further using significant figures, because we had 3 in the original. We had 50.0. So that's 3 significant figures. So we can just dumb this down to 25.6 meters per second. And that is our velocity at which this car can go without sliding up this curve. Without sliding up the angle, I mean. All right, thank you for watching. Thank you for taking the time.